All right, get ready because today we're taking a deep dive into a concept that'll really stretch your brain. Dualities. And you know what? I think you're going to love this.
Dualities are more than just fascinating mathematical quirks. They offer powerful tools for understanding the universe at its most fundamental level.
So what exactly is a duality? Think of it like if you're seeing one of those optical illusions where the same image, it could look like two totally different things.
That's a great analogy. Dualities in physics, particularly in string theory, are similar. They show us that things that appear completely different on the surface might actually be describing the same underlying reality.
Okay, that's already messing with my head a bit.
Yeah.
We're focusing on string theory today, right? What kinds of dualities pop up there?
Well, let's start with a classic example. Imagine a tiny closed string, like a little loop of energy, moving on a circle. Now, this string can wind around the circle, and it also has momentum as it travels along.
Okay, I think I can picture that. So where does the duality come in?
String theory says that a circle of a certain size, let's just call its radius r, is equivalent to a circle with a radius of 1, basically the inverse of the original size.
Wait, hold on. So you're telling me that a tiny circle is basically the same as a giant one from the string's perspective?
It does seem counterintuitive, I know, but the catch is that for these circles to be equivalent, we have to swap the string's winding number, how many times it's wrapped around the circle, with its momentum.
Okay, so the string's motion changes as the circle shrinks or expands. It's almost like the universe has this built-in zoom function.
That's a great way to think about it. And this type of duality, where we relate string theories on different size circles, is called T-duality.
T-duality, got it. So is that the only type of duality in string theory?
Not even close. We have other dualities, like S-duality, that work with a different set of variables.
All right, tell me more about S-duality then. How does it differ from the circle resizing T-duality?
Imagine we have a string theory, where the interactions between strings are very weak. It's like, imagine a cosmic dance floor where everyone's keeping their distance.
Got it. So like a very chill dance floor.
Exactly. But now, crank up the interaction strength, and suddenly the dance floor is packed. Everyone's bumping into each other. What S-duality tells us is that sometimes those two scenarios, the chill and the packed dance floors, can actually describe the same physics.
So it's like turning up the volume on those fundamental forces, but ending up with the same song, just played at a different intensity.
That's a good way to put it. It's like discovering that two seemingly unrelated pieces of music are actually variations on the same theme.
Okay, this is getting pretty wild. We've got T-duality swapping circle sizes and S-duality messing with the volume of interactions. What other kinds of dualities are lurking out there?
There are actually many others, and some of them connect different types of string theories themselves. String theory isn't just one single theory, it's more like a family of related theories.
A family of theories. So it's like string theory has cousins.
You could say that. And dualities reveal that some of these cousin theories might be more closely related than we initially thought.
All right, I am officially intrigued. Can you give me an example of how two string theories could be connected through duality?
Let's take type I string theory, which includes both open and closed strings, those little loops we talked about. Through duality, it's connected to something called SO32 heterotic string theory, which only involves closed strings.
Hold on. You're telling me that a theory with two kinds of strings can be dual to one with only one kind. That seems a little counterintuitive.
It does. But remember, dualities are all about finding those hidden connections. These two string theories, while they look different on the surface, might actually be describing the same underlying physics.
You're blowing my mind here. So these cousin string theories can be linked, but why do we even care?
Well, you've hit upon a crucial point. Why should we care about dualities? They're not just mathematical curiosities, they're incredibly powerful tools.
Okay, I'm all ears. Give me the why behind these mind-bending concepts.
Think of it this way. Imagine trying to solve a really complex puzzle. Dualities are like finding a secret cheat sheet that lets you translate that puzzle into a much simpler one.
A physics shortcut. I like where this is going. Tell me more.
String theory at strong coupling, where those interactions are super intense, it's notoriously difficult to study directly. It's like trying to have a conversation in a room full of screaming children. But S-duality can sometimes transform that problem into a much easier one by looking at its weakly coupled dual theory. Suddenly, it's like those screaming kids have calmed down and you can actually hear yourself think.
So dualities are like noise-canceling headphones for physicists.
That's one way to put it. They help us cut through the complexity and reveal the underlying structure of the universe. And they've also led to incredible breakthroughs in our understanding of some of the most mysterious objects out there.
Like what? Don't leave me hanging.
Black holes, for example. These enigmatic objects have puzzled scientists for decades. But by applying dualities, we can sometimes describe them in terms of more familiar objects, like strings and D-branes.
D-branes. Those sound familiar. They're like cosmic walls where open strings can attach, right?
Exactly.
Mm.
And by relating black holes to systems of D-branes, we can start to unravel their secrets, to understand how they work at a fundamental level.
All right, I'm starting to see why these dualities are such a big deal. They're like keys that unlock hidden doors in the universe. But I have to ask, where does it all lead? What's the future of dualities?
That's a question that keeps physicists up at night. One exciting avenue is exploring the connections between seemingly different physical theories. Maybe there's a grand unified theory out there, and dualities could help us find it.
A theory of everything. That would be incredible.
It would indeed. And another tantalizing possibility is that dualities could help us finally understand how gravity works at the quantum level, one of the biggest unsolved problems in physics today.
So these dualities can help us bridge the gap between the very large and the very small.
Precisely. They offer a glimpse into a deeper reality, where the universe's seemingly disparate parts are intricately connected. And who knows what other amazing discoveries await us. As we continue to explore this strange and wonderful world of dualities, it's a journey full of twists and turns, that's for sure. But that's what makes it so exciting. Always something new to uncover.
You know, I have to admit, I'm a little obsessed with this idea of the duality web. It's like a map of the string theory multiverse.
It is a bit like a map, showing how all these different string theories are connected through those dualities. And it's not just a pretty picture. This web has real implications for how we understand the universe.
Give me an example. How does this web actually help us make sense of things?
Well, remember those cousin string theories we talked about? One of those connections is between type I string theory and the SO32 heterotic string theory. Both of these theories involve these fascinating objects called D-branes.
Right, D-branes. Those cosmic walls where open strings can attach, but closed strings can pass right through them. It's like they're playing by different rules.
Exactly. And those D-branes play a crucial role in this particular duality. See, in type I string theory, you can have D-branes of different dimensions. Some are like strings, some are like sheets, and so on.
Okay, so different shapes of D-branes. What happens to them when we apply a duality?
Now, imagine we apply that T-duality transformation, the one where we relate different circle sizes. When you do that in type I string theory, it actually flips the dimensions of those D-branes.
So a D-brane that's shaped like a string could become a D-brane that's shaped like a sheet. That's pretty wild.
It is. And that flipping of dimensions, that intricate dance of the D-branes, helps us see how these two seemingly different string theories, type I and SO32 heterotic, are connected.
Okay, my brain is definitely doing some gymnastics here.
Yeah.
So dualities aren't just swapping sizes or changing the volume of interactions. They're also transforming the very objects that exist in these theories.
You're getting it. It's all about transformations and relationships, revealing these hidden symmetries and connections.
It makes me think that we humans, maybe we make things much more complicated than they actually are.
Perhaps we do. Now, are you ready to venture a bit further down this duality rabbit hole? We haven't even touched on M-theory yet.
M-theory. Okay, lay it on me. What is this mysterious M-theory? And how does it connect to everything we've been talking about?
Think of all these string theories we've been discussing, like type I and the heterotic theories, as different pieces of a puzzle. M-theory is like finding the box that holds all those pieces, revealing the bigger picture they create when assembled.
So M-theory is like the ultimate string theory, like the granddaddy of them all.
In a way, yes. One of the most amazing things about M-theory is that it suggests all the different string theories might actually be different aspects of the same underlying theory. It's like looking at a sculpture from different angles. Each view gives you a different perspective, but it's still the same sculpture.
Okay, that makes sense. But if M-theory is this unified theory, why do we even bother with all those separate string theories? Why not just focus on M-theory?
That's a great question. The truth is, M-theory is notoriously difficult to work with directly. It's like having a map of a vast, unexplored territory. You know it's out there, but actually navigating it is a whole other challenge.
String theories are like those more detailed regional maps. They help us explore specific areas of that larger M-theory landscape.
Exactly. And those dualities we've been talking about, they're like the overlapping sections of those maps, showing us how different regions connect, how different perspectives relate to each other.
It's all starting to click now. But tell me, with all these dualities linking different string theories and M-theory, does it ever get confusing? Like, how do physicists keep track of all these connections?
It's definitely complex. To keep things straight, physicists have constructed what they call the duality web. It's a visual representation of how all these different string theories and M-theory are related. It's kind of like a family tree. But instead of tracing ancestry, it traces theoretical connections.
Okay, the duality web. So physicists have their cheat sheet, right? But why should the rest of us care about all this?
Oh, well, remember, the duality web isn't just some abstract theoretical concept. It has real implications for how we understand the universe. For example, dualities have led to some incredible breakthroughs in our understanding of black holes.
Black holes. We did a whole deep dive on those a while back. I'm ready for a refresher.
Well, we've already talked about how S-duality can be used to study those super dense black holes, where the interactions are really strong. But dualities do much more than that. In some cases, they suggest that black holes might actually be equivalent to collections of D-branes.
Wait, what? How is that even possible? Black holes are these massive, dense objects. How can they be the same as those D-branes, those cosmic walls we were talking about?
It all comes down to how we count the microscopic degrees of freedom of these objects. In string theory, a black hole's entropy, which is a measure of its internal disorder, is related to the number of ways you can arrange those tiny stringy constituents.
Okay, so the more ways to rearrange those little string bits, the higher the black hole's entropy.
Exactly. And it turns out that the entropy of a black hole, calculated using string theory, can be precisely matched to the entropy of a corresponding system of D-branes. It's one of the most profound results in string theory, and a major piece of evidence supporting the idea of dualities.
So it's like those two sides of the same coin again. The same underlying reality, just described in two completely different ways. But tell me, do these dualities have any practical applications beyond helping us understand black holes? Can they help us create new technologies, for example?
That's a question a lot of people ask, and it's an area of active research. While we're not building duality-powered spaceships just yet, dualities are proving incredibly useful in other areas of physics, like condensed matter physics.
Condensed matter physics, that's the study of materials and their properties, right?
Yeah.
What do dualities have to do with that?
More than you might think. They're helping researchers study some really exotic states of matter, like superfluids and superconductors. You remember those, bro?
Of course. Superfluids, those liquids that flow without any resistance. And superconductors, those materials that conduct electricity with zero loss. We did a deep dive on those too.
And the same mathematical tools used to study dualities in string theory are now being applied to understand these complex systems in condensed matter physics.
So string theory is spilling over into other areas of science. That's amazing.
It is. It's a testament to the interconnectedness of scientific knowledge and how seemingly abstract theoretical ideas can have unexpected real-world applications.
This is what I love about these deep dives. You never know where they're going to lead. But right now, I'm really curious about one thing. Can these dualities help us tackle the biggest challenge in physics today? Unifying quantum mechanics and general relativity.
Ah, yes, the holy grail of modern physics. It's the quest to understand how gravity works at the quantum level. And you know what? Dualities might just hold the key.
Okay, you've got my attention. Tell me more.
One of the biggest hurdles in unifying these two theories is that they operate on vastly different scales. Quantum mechanics governs the world of the very small. Atoms, particles, the quantum realm. General relativity, on the other hand, reigns over the world of the very large. Planets, stars, galaxies, the fabric of spacetime.
It's like trying to make the rules of a board game work for the entire universe.
Exactly. But dualities offer a potential bridge between these two seemingly incompatible worlds. One approach, called the SCFT correspondence, relates a theory of gravity in a particular type of spacetime, called anti-de Sitter space, ADS, to a certain kind of quantum field theory, CFT, that lives on the boundary of that space.
So you're telling me that a theory with gravity is equivalent to a theory without gravity, in one fewer dimension.
It sounds crazy, right? But that's the beauty of dualities. They push us to rethink our assumptions about how the universe works. This ADA-CFT correspondence suggests that gravity might emerge from a more fundamental non-gravitational theory in a lower dimension. It's like a holographic projection. The information about the higher dimensional gravitational theory is encoded on the lower dimensional boundary.
Holographic gravity, that's wild.
It is. And what's even more exciting is that this ADA-CFT correspondence has passed a lot of theoretical tests. It's even given us new insights into the behavior of those strongly coupled quantum systems we were talking about earlier, like those found in condensed matter physics.
So it's not just about unifying gravity and quantum mechanics. It's also about understanding those extreme and mysterious phenomena in the universe.
Absolutely. Black holes, the Big Bang, the very nature of space-time itself. Dualities are giving us powerful new tools to explore these mind-boggling concepts.
You know, I'm starting to think that dualities are kind of like those choose-your-own-adventure books. They open up all these different paths to explore, all these different ways of understanding the universe.
I love that analogy. And the best part is, we're just beginning to explore those paths. There's so much more to discover.
Speaking of discoveries, I'm dying to know, what are the biggest unsolved mysteries that dualities might help us crack? What's next on the horizon for these amazing theoretical tools?
Well, for starters, the true nature of M-theory itself is still a mystery. We have glimpses of its structure, its potential to unify all those string theories, but a complete formulation remains elusive.
It's like we found a treasure map, but we're still searching for the buried treasure.
That's a great way to put it. And then there's the whole mystery of dark matter and dark energy. These mysterious entities make up the vast majority of the universe's mass and energy, but we still have no idea what they are.
Right. It's like the universe is playing hide and seek with us.
Maybe dualities can provide some new clues, new ways to detect these elusive components of the cosmos. Some physicists even think dualities might point towards the existence of extra dimensions, beyond the 3 spatial dimensions we experience every day.
Extra dimensions. That sounds like something straight out of science fiction. But honestly, with dualities, nothing surprises me anymore.
That's the spirit. Keep an open mind. Because with dualities, the possibilities are endless.
All right, before we go any further down this rabbit hole, let's take a step back and talk about something we touched on earlier. The idea that dualities provide a microscopic explanation for black holes. I'd love to hear more about that.
Of course. You see, before quantum mechanics came along, black holes were thought to be these cosmic vacuum cleaners, these bottomless pits where nothing could escape. But then, in the 1970s, Stephen Hawking came along and showed that black holes actually emit radiation due to quantum effects near their event horizon.
Right, Hawking radiation. That discovery really changed how we thought about black holes.
It did, but it also created a new puzzle, the puzzle of black hole entropy. See, in thermodynamics, entropy is a measure of disorder or randomness. It's like how many different ways you can rearrange the molecules in a gas without changing its overall state.
Got it. The more ways to rearrange things, the higher the entropy.
Exactly. And according to Hawking's calculations, black holes have incredibly high entropy, proportional to the area of their event horizon. But here's the catch. Classical physics had no explanation for what those microscopic degrees of freedom, the things being rearranged, actually were.
So we knew black holes were messy, but we didn't know what was making the mess.
That's a great way to put it. And that's where string theory and dualities came in. They provided a framework for understanding those microscopic degrees of freedom.
Okay, I'm intrigued. How did they do that?
Remember those D-branes? The ones that act like walls for open strings. Well, it turns out those strings attached to the D-branes can vibrate in many different ways, just like the strings on a guitar. And each different vibration corresponds to a different quantum state.
So it's like those strings are playing a cosmic symphony, and each note contributes to the black hole's entropy.
That's a beautiful analogy. And by carefully counting those different string vibrations, physicists were able to reproduce the exact entropy of the black hole, matching Hawking's calculations. It was a huge win for string theory and dualities, showing that they can really shed light on some of the most profound mysteries in physics.
All right, my mind is officially blown. Dualities are not only fascinating, they're also incredibly powerful tools for understanding the universe. But you know what? There's something even more mind-boggling about all this.
What's that?
This interconnectedness of string theories and M-theory, this duality web, it's almost as if the universe is trying to tell us something profound about the nature of reality itself.
It's a truly remarkable thought, isn't it, that there might be a deeper truth, an underlying principle that connects everything in ways we're only beginning to grasp. And it's a thought that motivates physicists to keep exploring, to keep pushing the boundaries of knowledge.
Well, on that inspiring note, I think it's time to wrap up this incredible deep dive. But before we do, I'd love to hear your final thoughts. What's one mind-bending nugget of wisdom you'd like to leave our listeners with?
Dualities show us that reality is full of surprises, full of hidden connections, unexpected relationships. They challenge us to question our assumptions, to embrace new perspectives, and to see the world in a fundamentally different light. So my challenge to you, dear listener, is this. What other dualities might exist in the way you view the world around you? What seemingly opposite ideas, concepts, or experiences might actually be two sides of the same coin?
It's like, we started this whole deep dive talking about optical illusions, right? And how
Yeah.
the same image can look like two totally different things. And now,
Yeah.
after exploring all these dualities, I'm kind of starting to feel like the whole universe is one giant optical illusion.
I think there's something to that. Dualities really do challenge our perceptions of reality. They show us that there isn't necessarily one single correct way to view the universe. Instead, there might be multiple, seemingly contradictory perspectives that are all equally valid.
So it's like, are you saying that the universe is inherently ambiguous? That
No.
there's not always a simple, clear-cut answer?
It is a bit unsettling, isn't it? But it's also incredibly liberating. It means that we're not limited by our preconceived notions. We can explore all these different perspectives, all these different ways of understanding the universe.
Yeah, it's like we're given permission to think outside the box, to embrace the weirdness and the wonder of it all. And, maybe that's the key to unlocking even deeper truths about the universe.
I think you're right. Dualities remind us that the universe is full of surprises, full of hidden connections, and unexpected relationships. And the more we explore those connections, the more we realize just how much we don't know.
And that's what makes it so exciting. There's always something new to discover, always a new mystery to unravel. And I have a feeling that dualities are going to continue to guide us on that journey of discovery for many years to come.
I couldn't agree more. And who knows, maybe someday we'll even be able to harness the power of dualities to create new technologies, to solve some of the world's most pressing problems. The possibilities are truly endless.
Well, on that note of cosmic optimism, I think it's time to wrap up this incredible deep dive into the mind-bending world of duality.
It's been a pleasure exploring these ideas with you.
And to all of you listening out there, a huge thank you for joining us on this journey. We hope you've learned something new, and we hope you'll keep questioning, keep exploring, and keep your minds open to the universe's infinite possibilities. Until next time, keep diving deep.